This isn't about finding some incorrect results in the published literature. Tell us a little bit more about that and why you think they're incorrect.
We simulated like the 3-line one. We got that it started forming quantum dots, and rings started forming around them. But in the papers, they began to form really strange serpentine stripes, which may be correct, may be incorrect, we don't know. But like from our simulations, we got that. Okay, here's an actually good example. There's one simulation we did where it was homogeneous, and it became really refined on the edges of all the patterns. But we really weren't paying attention. But we noticed that when we ran only one time step, the pattern suddenly switched places. Like the high concentration and the low concentration just switched. But we use the exact same variables as they did, and we think that's because of numeric error.
That's a good, that flip-flop is numerical instability, very likely, yes.
So in exploring, I mean, the whole point of this is to find heterogeneous patterns that lead to interesting circuits constructions. Did you explore patterns, I mean, heterogeneous patterns that you hadn't found in the literature, or did you just stick to replicating things that hit them?
We did that too, but the circle we didn't find in the literature. We also ran one with a pentagon, and it was interesting. It was almost like a circle, except it didn't have as much of the spreading. We looked at a square, which we think, I think that was in the literature. We didn't look at as many results as we expected to, but we did some results that were different in the literature.
You talked about using the semi-implicit method and its advantages over implicit and explicit, but you didn't mention any shortcomings in that method. Are there any that you had to deal with?
Not any that we had to deal with, but it's like all numeric methods, it's unstable at some points.
And then you talked about in future we're going to fully implicit because you could increase the time step. So is that what you might consider a drawback of semi-implicit, that the time steps are so small?
Semi-implicit time steps could be better than explicit, but they're not as good as implicit. So they're kind of in between, and we plan to make it do it as best as possible. Any more questions?
Well, I only have an observation. I've been thinking about these problems, and you made a presentation at the academy, and then because overall this is a deterministic technique, to solve your problem. It's a very complicated equation, all of that, for a problem that in nature is probabilistic. See, when you go into very close to the quantum range, there are certain kind of perturbation, even when they're getting together the molecules to form the secret. It's a quantum problem. It's sort of semi-classical problem, but there are certain quantum effects there that make it, so certain degree of randomness in that. And so what I see in the problem that you mentioned, the instability, it could be you show 10 to minus 4 to 10 to minus 3 range of your parameter to get the stability there. So it's sort of a recipe you have there, right? But that parameter has to be explained in those terms, in quantum terms. So you are getting in those dimensions, that's why I'm trying to explain that. So probably that somebody is going to figure out an approach, that is semi-classical,
Yeah, it might be interesting to see the results if they did put some randomness in there. I don't know where.
Yeah.
Understand their model enough and see how much you get. If that, if, you know, if that little bit of randomness gave you some wild swing in the output.
That's right.
The quantum effects you're talking about, but there doesn't seem to be, I didn't see any quantum mechanism in the model.
Right.
Is that, am I missing something?
We think that this model doesn't incorporate all the quantum effects.
Does it incorporate any quantum effects?
I don't think so.
Yeah, this.
I don't know.
Yeah, that's true.
We're still on a nanometer scale.
Yeah, quantum.
Yeah, like the simulations were 50 nanometers wide. So I know that the quantum should come in there, but I mean, we're not talking about on the scale of the molecule.
That's right. Then why are they called quantum dots?
Oh, no, that's just because they're little dots.
But actually,
That was my question, because I said, this doesn't sound, these don't look like the quantum dots I've heard about before.
I think these are called quantum dots because at that level, with all those dots, you can actually see quantum effects. That's what we've learned. We can't really explain that much, but also one thing I forgot is that for quantum dots, the temperature, as they get bigger, their physical and chemical properties change. But yeah, I think it's the reason why they're called quantum dots because you can see the quantum effects.
But they're still 2 or 3 nanometers wide.
Right.
Okay, thank you very much.